Yeah, so today I'm going to talk about beyond the first portrait of a black hole. But before I get into that, I want to talk a bit about imaging the invisible, which, is very familiar to a bunch of you, I'm sure. So many things, that we want to take images are invisible to us. So for instance, one that might be familiar to you is we can't take a picture of our brain using a standard camera. And in these cases, since it's impossible to directly image the thing we want to see, we have to develop alternative ways to take indirect measurements, for instance, using an MRI scanner. In these cases, the measurements don't look anything like the image we're trying to capture, and so we have to design algorithms that work with the new sensing system in order to recover the desired picture. And as you all know, this isn't just true in medical imaging, but in a range of many different applications, this field referred to as computational imaging or computational photography. And as just an example, using this methodology, my group has been working on developing techniques to estimate an object's material properties, and improve medical imaging, and see under the ground. But today I'm going to talk about how we can use computational imaging to reveal what I think of as being the ultimate invisible, black holes. So black holes are one of the most mysterious phenomena in the universe, and scientists have been studying them ever since they were first predicted from Einstein's theory of general relativity just over 100 years ago. In particular, for decades, scientists have been studying this giant elliptical galaxy that's at the head of the Virgo constellation. And this galaxy is called M87. It's 55 million light years away from us and very special because over 100 years ago, someone discovered that there was this streak of light on the sky, which ended up being a galactic scale jet of plasma that was shooting out of the core of the galaxy and marking the spot of a supermassive black hole. And so over decades, scientists tried to develop better and better instruments to study the supermassive black hole predicted to be at its center. And then in April of 2017, we hooked up that Earth-sized telescope and collected the data necessary to make the very first picture of a black hole. And 2 years later, after processing the data, this is what we saw. So this ring of light is a signature of a black hole's event horizon. But since it's so far away from us, it appears incredibly small in the sky. It appears about the same size as a grain of sand, but if that grain of sand is in New York and I'm viewing it from where I am at Caltech around Los Angeles. And so taking a picture of something that small required an international collaboration of scientists from all around the world building new instruments and algorithms to make it possible. So I know I gave a talk on the imaging of black holes previously at EPFL, and so I don't want to rehash everything that I said then. But today I do want to tell you a very brief story of how we were able to take a picture of a black hole, and then that will help in motivating the majority of the talk today, where I'm going to talk a bit about techniques currently being developed in my group at Caltech to push the imaging of black holes past their current limits to see things that are still invisible to us. In particular, I'm going to be talking about new machine learning approaches my group is developing for doing uncertainty quantification of images and computational imaging systems, as well as how we're developing approaches to recover the dynamics of a black hole over the course of a night. So because the black hole's shadow, that ring of light, is so small and can be only seen at a very particular wavelength, diffraction limits required that we build a telescope 13 million meters in size to see that event horizon scale structure. 13 million meters, or essentially the size of the Earth. And although we couldn't build a single dish telescope the size of the Earth, the Event Horizon Telescope collaboration instead spent well over a decade joining telescopes located around the world to build a computational telescope the size of the Earth, capable of resolving structure on the scale of a black hole's event horizon for the first time. So how does this computational telescope work? Well, unlike with a camera, in the Event Horizon Telescope, we don't capture the picture in pixel space, but instead in its frequency space. So we essentially are going to be taking measurements of the black hole image's Fourier transform. And if we put telescopes all across the globe, we would sample all these spatial frequency measurements. However, since we only have telescopes at a few locations, that means we only get a sparse number of measurements. And so it turns out that for every 2 telescopes in our telescope array, we obtain a single complex measurement of the underlying image's 2D spatial frequency that's related to the projected baseline between the telescopes. But if we only have a small number of telescopes, then we have a very small number of measurements. If we only have 5 telescopes, then that's only 5 choose 2, 10 measurements that we have to work with. But luckily, as the Earth is rotating, we actually obtain other new measurements. So since the projected baselines between the telescopes change as the Earth rotates, This amounts to carving out different elliptical paths in the spatial frequency plane. So how do we make an image after extracting these measurements? Well, at this point, we have the data, and so we can kind of abstract away the astrophysics of the problem and look at it as a purely mathematical inverse problem. We have the sparse data, and our challenge is to invert the measurements to find the image that caused it. And if we were given measurements that covered the entire frequency plane, it would be trivial because in the case of no noise, you would just simply need to apply an inverse Fourier transform to the measurements to recover back the picture. But since we only see a few samples, there are therefore an infinite number of possible images that are perfectly consistent with the data we measure. And on top of that, the fact that there's a different and quickly changing atmosphere above each telescope across the globe causes our data to be very noisy, and the problem becomes even more ill-posed. So to solve for the black hole image, we had to develop a number of techniques to handle this challenging inverse problem. One of these techniques we refer to generally as regularized maximum likelihood estimation, which I'm sure you all are familiar with as a general idea, but just to briefly summarize the approach, we modeled the forward telescope system as a function f of x that returns the data we would likely see, y hat, if the true image in the sky were x. However, since we do not observe all the possible measurements, since we have sparse data, that means that there will still be an infinite number of images that will give us exactly the same y hat, making that the problem ill-posed. However, although there are an infinite number of solutions that are equally likely in terms of the measurement likelihood, of the images that are consistent with the measured data, there are some images that we consider more likely than others. For instance, perhaps we think that the image on the left is too messy, and we prefer images that are sparse or compact. Thus, our goal becomes to find an image that doesn't just fit the data, but is likely under some sort of model of good or likely images, some mathematical model of this. And so using this idea, we incorporated what we call an image prior that essentially scores the images. And by solving for an image that maximizes both the data likelihood and the prior, we can whittle down from the infinite possibilities to a single one that we think is a likely image that fits the data well, even in the presence of all the kind of crazy noise that we experience. Okay, because it's going to come in handy later, I want to remind you mathematically what this looks like. So we're solving an optimization problem where we're trying to find an image x that maximizes the posterior probability conditioned on the observed measurements y. And by simply rewriting this using Bayes' rule, we can see that maximizing this log posterior probability is equivalent to maximizing the sum over the data log likelihood and the log image prior, those two terms that I just discussed in a super hand-wavy way. But note that even if we can develop these methods such as these that allow us to recover a single image, we always have to be really cautious. And that's because any method that we come up with, whether it's a regularized maximum likelihood approach like I'm showing here, or a fancy new machine learning approach, no matter what, it's going to require that we inject some additional information into the problem about what images look like to recover something back in the end. In the case of the regularized maximum likelihood problem, it's through the prior, highlighted in yellow. And this injection of additional information always is going to bias our final picture. And for instance, we wanted to be really careful about this because the whole point of the Event Horizon Telescope was to test, do we see this ring? Or that was the primary objective. And we wouldn't want to accidentally have a preference for ring images and then be super excited that we recovered a ring back in the end. And that meant the big question we faced in dealing with the M87 black hole data was not just how to make an image, but how do we verify what we're reconstructing with our imaging algorithms is real? And we tackled this by approaching the imaging problem in many different ways. One way we tackled it is by developing 3 different imaging pipelines. These pipelines are online, so you can download them along with the data, and you can run the methods and develop your own approaches. And we designed these pipelines to have different hyperparameter knobs on them that control modeling and optimization choices that are used when solving for the best image. Typically, these hyperparameters are tuned by a human user. But instead of having a human tune them, we instead wanted to search for the best set of knobs to recover different kinds of source structures and then see how those settings then influence the M87 images that we recovered. For instance, we generated synthetic data as if the Event Horizon Telescope were actually seeing a disk on the sky that had no hole in the center, and then we searched for the best parameters, beta here, to recover this disk shape. Then when transferring these exact parameters onto the M87 data, we found that although we had tried our hardest to find parameters that recovered a disk with no hole, our algorithm still required us to put a hole in the center when using the real data. And so by doing this simple training and testing procedure on many different types of underlying sources, we saw that our methods always preferred that ring shape, and that was true no matter the day we observed M87 on or the imaging code we used to reconstruct it. And so by blurring the images from different imaging pipelines to an equivalent resolution, we then averaged them to form the image that we showed everyone back in 2019, that ring of light surrounding the black hole, roughly 40 microarcseconds in size and brighter on the bottom than the top. So our goal here was to try to remove human bias from the final image as much as possible and use very simple training data to select hyperparameter modeling choices. And this prevented us from tweaking parameters too much by hand to get an image that we wanted in the end, even if it was just subconscious. And by doing this, we did get this ring shape, which was incredibly exciting. However, this doesn't answer the question of what is the uncertainty in the image? How likely is this ring? Did we just again get lucky with these particular parameter choices? So how did we go about doing that? So previously I talked about how we selected one set of parameters, beta, that performed best on synthetic data. But why should there only be one parameter set that we consider? In fact, by doing large parameter surveys, we found that there are often many parameters that actually perform reasonably well on the synthetic data sets that we had come up with. So instead of setting just one set of betas, we instead set a threshold and found all the beta parameters that performed above that threshold on the synthetic data. So for example, for one of the imaging pipelines, we ran hundreds of thousands of simulations and found we had about 1,500 parameters that we deemed acceptable. Once we had decided these 1,500 parameters from the synthetic data, we then transferred them onto the real M87 data to see what would happen, what was the resulting images, and how did they vary? So here is showing the results of applying those 1,500 different parameters onto the M87 data. On the left, you're showing this is the mean image, the average image we obtained from those 1,500 different parameters. And in the center is the standard deviation. The standard deviation tells us where there are variations. And you can see that along the ring, there are these 3 knot regions that are brighter than the rest of the ring. And so those areas are less constrained. However, if you look at the fractional standard deviation, you'll see that the standard deviation is much smaller than the mean of the image. And so actually, although along the ring, there are areas that we have more or less certainty in their particular intensity value, that ring actually was in basically all the images that reconstructed, but what differed a lot was actually all that wispy structure on the outside that you shouldn't believe. So this gave us one way of characterizing the uncertainty in our image. But I want to strongly highlight that what we're doing here was probing different modeling choices and then seeing how that affected our results. So in the regularized maximum likelihood problem, we were essentially changing something like our prior term and then seeing how that prior affected our results. And that is definitely something that's important to explore because we do have uncertainty in what that prior should be. As I talked about, we didn't know what the prior of a black hole image should be ahead of time. But it's important to note that this is not a posterior distribution. It's not directly quantifying uncertainty due to the data under a fixed prior model. So going forward, it would be great if we could efficiently explore uncertainty, not only due to the prior, but also due to the data fit. In other words, we would love to be able to sample from our posterior distribution directly under a fixed prior assumption and see how that affected our results. But how should we go about doing that? Well, one natural approach would be to use something like a Markov chain Monte Carlo method or some other kind of sampling method. However, these sampling methods are notoriously slow because as you increase the dimension of X, the image size, it takes so long in order to make sure that you've converged. And so even for something like a 10 parameter model that we've analyzed in the past, it can take a whole day for a sampling approach to converge, let alone an image that with hundreds to thousands of parameters. And so to tackle this, we recently have been developing new methods for efficient posterior exploration by exploiting deep learning machinery. So let's start by revisiting the deep generative model, and you'll see why in a minute. So, of course, many of you might be very intimately familiar with the great success of deep generative models in computer vision and machine learning. So what are these? So given enough training images, we can train a neural network that takes as input random noise and then outputs a picture that looks like a real scene at first glance. And by plugging in different noise images, you'll get different output pictures. So why am I telling you this? Well, these deep neural networks define an implicit distribution over the space of images. And the impressive results we witness with the generative models indicate that these networks allow us to learn very flexible and expressive distributions that capture complex correlations in pixels. So inspired by these generative models, my postdoc Hassan and I have been developing an approach to sample from a posterior distribution using a learned generative neural network. So our goal here is to learn the weights phi of a neural network such that if you pass different random noise to the neural network, out is going to pop a sample from the image reconstruction posterior. Different input noise is going to result in different posterior sample images. So essentially this neural network, the goal of this neural network is just to learn a mapping from a noise distribution to the target image posterior distribution, the reconstruction image posterior. Okay, so how should we go about training a network to give us posterior samples? Well, unlike in the case of the bedroom generator, we don't actually have a set of training images to use. If we did, if we had a set of samples from the image reconstruction posterior, then we would be done, right? Because there would be no need to learn a neural network to generate samples if we already have samples from the posterior. The only data we have for optimizing the neural network is the sparse and noisy measurement data Y of a single hidden image. So in our approach, which we call deep probabilistic imaging or DPI, instead of using a collection of training images to solve for the neural network, as is typically done in other computer vision problems, we instead define the loss to be the KL divergence between the distribution learned by the generative model and the true image posterior. So we want to maximize the similarity between these two distributions. This particular loss makes deep probabilistic imaging a special type of a variational inference method. So as a reminder, in variational methods, we define a simple family of density functions, for instance, Q phi here, visualized by the blue space of possible distributions, and then we solve an optimization problem to find the parameters phi that best match the target posterior distribution we're after, that gold star here. But then the question always becomes, what should the family of variational distributions be? Traditionally, they're typically pretty simple, so you can solve the necessary integrals by efficiently evaluate probabilities. So a lot of times, simple distribution families like Gaussian distributions are used. But in DPI, by using a neural network, we can define a very flexible family of distributions that are parameterized by phi, which are just the network weights. And this flexible family of distributions can better capture the image posterior distribution that we're interested in targeting. So really all the neural network does here is it gives us the flexibility we didn't have before with the simple variational methods. And this allows us to get much closer to faithfully approximating samples from a well-defined posterior distribution. Actually, DPI's optimization problem can also be intuitively derived by extending the regularized maximum likelihood estimation method. So to show you how this is the case, let's instead optimize the neural network weights phi so that every time we sample a new image x from this network, the posterior likelihood of that sample is high, conditioned on the observed measurement. So we want to find a network phi here that gives us that produces images that have a high likelihood. And simply rewriting this using Bayes' rule, we want to again see how we can split that posterior into a data likelihood term and an image prior term, just like the maximum likelihood approach. So overall, this is looking very similar to the regularized maximum likelihood optimization problem that we talked about earlier. Just now we're taking an expectation over the image samples from our neural network rather than just solving for one image. Okay, well that kind of makes sense. This is going to solve for a network that will produce images that have a high posterior likelihood. But there's a catch. And that's that this is not going to sample images from the posterior. It's just going to collapse to a single deterministic solution. It's going to find network weights to always produce the image that scores best under this loss. And that's not what we want because it's not capturing the uncertainty in our reconstruction. So what should we do instead? Well, it turns out that in order to avoid this mode collapse problem, we can include an extra entropy term to encourage the diversity of the generative samples from the neural network. So we add this additional term here on the end that is just trying to increase entropy of the distribution. And this prevents the network from collapsing and only producing a single image, since it wants to make sure that the neural network's image distribution has entropy, that the images that are produced by that distribution have some diversity to them. So what I've said might sound intuitive, but still pretty hacky. But actually, this solution has a solid mathematical foundation because this intuitive loss turns out to be exactly the same as the Kale divergence between the generative model distribution and the image posterior that we started with at the very beginning. So that means in addition to understanding DPI as a variational inference method, it can also be regarded as a natural extension to doing uncertainty quantification for regularized maximum likelihood estimation problems. Okay, great. But one thing that I think is worth noting here is that in order to optimize this loss function, we need our generative model to be efficient in both generating samples and evaluating the likelihood of some arbitrary image. However, normal generative models like GANs and BAs are only good at generating samples, but cannot evaluate a sample's likelihood to compute that entropy loss that we need at the end. So in order to accomplish both goals in DPI, we use an invertible generative model called a normalizing flow network. And this type of network can be executed in both directions. And as a result, we can easily generate samples from noise using the forward pass and then easily compute the entropy loss using the inverse pass. Okay, so we've tested this approach in multiple cases, but due to time, I'm only going to briefly show a couple examples I find instructive. So here's an example. On the top is a synthetic image of a black hole. And we took this image and we generated synthetic data from it as if the Event Horizon Telescope were actually seeing this distribution of flux on the sky. And using this mock data set, we then ran our typical regularized maximum likelihood methods to see what result we got. And we noticed that every time we ran the method with slightly different initialization, so we'd start the method off with a slightly different image, and we would recover different results. In some images, the bright spot was in the top right, and in some cases, the bright spot was in the bottom left. And it actually appeared that both modes fit the data well, and so by just looking at that, it was hard to determine which one was the correct mode without knowing what the truth is, right? And this ends up not being that rare of an occurrence in black hole imaging problems, and that's because of the crazy noise that we experience in our measurements. We actually have to solve a non-convex optimization problem that sometimes has multiple solutions. So we tested our deep probabilistic imaging algorithm on this data set to see what we would learn from an approximate posterior distribution. And on the bottom right are some samples from the learned neural network. So remember, we have one data set. From that one data set, we optimize the weights of a neural network. Once we've optimized those weights, all we need to do is pass in noise to the neural network to sample different posterior estimates. And so just a random sampling are shown on the bottom right. And so you can see that our learned neural network was able to capture a posterior distribution that also indicates there are two modes in our data. But perhaps the most interesting thing is what happens when we run it on some real data. So this is a result we got when we ran the approach on the real M87 black hole data. And what I find really encouraging is that if you compare the standard deviation in the resulting images to the standard deviation we had published earlier, you can see that they're actually amazingly similar. Although these standard deviation maps represent slightly different things, they're still comparable in what they're saying that we're uncertain in. So in both uncertainty maps, there are 3 regions with the highest uncertainty that seem to match up. And so this was super exciting to me when I saw this result, since actually the very first time He ran the method on the real M87 black hole data, he got nearly the same result that it took an entire group of scientists from around the world months to achieve through these grueling parameter surveys that I talked about before. And it only took about 1 hour of training time on a single GPU. So I'm really excited to be making progress on methods that allow us to better understand our uncertainty in computational imaging systems more efficiently. And as it turns out, we've found that this DPI framework is not just useful for black hole imaging, but very useful for many different types of problems. So here are just a few of the applications we've been using it on in our group, from medical imaging to exoplanet orbit fitting. Unfortunately, I don't have time to go through all of them today, but I hope have another time to show you how deep probabilistic imaging is helping in all these other exciting areas. But for now, let's just get back to the black hole. So the story of M87. So from many different angles, we've recovered this image of the light circling the black hole. And this image tells us so much about the immediate environment around a black hole, and it helps us get a better constraints on our understanding of gravity, testing general relativity, and so forth. But perhaps the most amazing thing is that, by comparing this picture to simulations scientists have made for years, we find that the image that we have taken, that we've made, is amazingly consistent with a number of these predictions. But you might notice that the simulation I just showed you, it was moving. So you might wonder, is our recovered image of M87 also moving? And in fact, it turns out that it is. So another interesting thing is that we actually collected data from the M87 black hole over the course of an entire week, 2 days at the beginning of the week and 2 days at the end. And we independently reconstructed each of these days of data, and then we could string them together to form a short movie. And if you play them as a movie, you'll see that there is some evolution there. So I'll play it for you now. It's pretty hard to see, so I'm going to do it again. You'll see that the bright spot moves more from the left side, more down to the bottom. So studying evolution like this is quite exciting. It not only gives us a window into the dynamics around a black hole and hopefully an understanding of how their powerful galactic scale jets are forming, but it also helps us in mapping the space-time of a black hole and constraining our prediction of general relativity even further. But actually, the black hole in M87 is not the only black hole we're interested in imaging to get a handle on the question of time variability. In the heart of our own Milky Way galaxy, 26,000 light years away from us, there's this cluster of stars. And by peering past all the galactic dust with infrared telescopes, astronomers have mapped the paths of this cluster of stars over decades. And by tracking the motions of the stars over time, astronomers have concluded that the only thing small and dense enough to cause this motion is a supermassive black hole. In fact, this discovery led to the Nobel Prize in Physics given last year for the work of Andrea Ghez and Reinhard Genzel for the discovery of a supermassive compact object at the center of our galaxy, otherwise known as Sagittarius A star. So as awesome as M87 has been, Sagittarius A star, or like we like to call Sag A star for short, might be able to help us better answer these questions. So Sag A star is teeny tiny compared to M87. M87 is 6.5 billion solar masses, and Sag A star is a measly 4 million solar masses, but because it's much closer to us, it appears about the same size in the sky. But since it actually is physically smaller, that means gas orbits around it much more quickly. So whereas it takes 4 to 30 days for gas to make a complete orbit around M87, for Sag A star, it makes a full orbit every 4 to 30 minutes. And so we'd love to be able to image the time variations around Sag A star, but doing so is difficult. Why is that? Well, remember, in the case of M87, it's essentially static over the course of a night as the Earth is rotating. And that means as the Earth is rotating and the spatial frequencies are being swept out, all the measurements that we make all kind of correspond to the same picture in the sky. So we can throw all those measurements into one big pot and use it to form one image. But since in Sag A star, it's actually evolving on the time span of minutes, that means that every measurement we make is from a different snapshot of the black hole. We're just seeing different frames of a black hole moving. And so how should we capture that black hole's evolution? Well, if we were just to apply the same static imaging methods as before and try to reconstruct each snapshot using the small number of measurements seen at each time, then the data is just far too sparse to use this approach, and it results in uninformative images. So clearly this naive snapshot approach doesn't work. And so instead, we've been developing methods to try to recover not just static images from the data, but also information about the underlying dynamics. The first approach we took was to develop methods to reconstruct full movies of the black hole evolving over time. However, if you thought recovering a static image was a hard, ill-posed problem, this is orders of magnitude more challenging because we have the same amount of data, but now we have to solve for the pixels in a full movie rather than just a single frame. And so to get around this, you often have to include a significant amount of temporal regularization into the optimization problem in order to get a good result. Basically, you help reduce the space of possible movies that could fit the data by saying that adjacent frames that you reconstruct should look similar to each other. So this prior encourages smooth evolution of the black hole over time. But oftentimes you have to crank that regularization up so much that oftentimes the reconstruction that you make is missing all the rich dynamics that you're really after. So here on the left shows a synthetic ground truth video, and on the right, the video reconstruction obtained from this method, assuming that measurements from the EHT array. Okay, so this is a lot of improvement over the random gibberish that I just showed you before, but it's still not really what we want. Now we've reconstructed something like the average structure, and we see a little bit of evolution, but it's lost all the information about how gas is actually flowing around the black hole, and the dynamics are almost all lost. So although imaging is crucial in making sure we give ourselves the flexibility to see something surprising, perhaps if our ultimate goal is to understand the underlying motion field, this isn't the right approach. So for instance, maybe we want to instead recover something like the parameters of a persistent motion field. So looking at this movie, the simplest thing you might want to recover is something like which direction is the gas spinning, clockwise or counterclockwise. However, more generically, we could try to recover an underlying flow field that describes the evolution in the source, similar to doing something like optical flow. So a non-parametric flow field like this would give us the flexibility to describe arbitrary evolution in the underlying source. Gives you lots of flexibility. Alternatively, you could also imagine wanting to describe the underlying flow using a physical model of black holes. For instance, we could search in the space of parameters that produce different synthetic black hole videos and try to find the parameter settings that best match the data we've observed. And while this theoretically may be possible to do, in reality, it is too computationally expensive because simulating just 60,000 static image snapshots of the black hole for the M87 papers that we published a couple years ago actually took over 75 million core hours to compute just for those 60,000. So it's not something that we would be able to naively search over using just something like some sort of MCMC sampling method. So there's this whole spectrum of different approaches that one can take in trying to recover the underlying motion of a source. On one end is recovering a non-parametric flow field, which is maximally flexible, but requires this to recover a movie of flow fields. And in the end, it's not necessarily very interpretable. And on the other end of the spectrum is estimating the parameters of a physics-based black hole model. And while this result would be maximally interpretable, this approach has the disadvantage that we're tied to a black hole model that's not necessarily correct and therefore overly restrictive. So rather than picking one of these extreme options, we'd like to find some sort of middle ground, using a model that balances the pros and cons of these different approaches while being computational efficient. And towards that end, we've been working on modeling the persistent evolution of black hole sources as a result of a stochastic advection-diffusion process, and solving for the underlying parameters of this model that best fit the observed measurements. So this intermediate option tries to find a compression of the motion field by asking us to only match the persistent motion statistics. This work is being led by Aviad Levis, who's a postdoc in my group, in addition to our black hole theorist collaborators, David Lee and Charles Gammy from UIC, and then also Joel Trop from Caltech. So let's dive in to understand a little bit better. So here I show the equation of a stochastic partial differential equation, PDE, describing an advection-diffusion process. Don't worry about trying to understand the equation. I'll just point out the parts that are important for you to understand. So in this process, there are two parameters we really care about, V and D, where V is the velocity field that describes how the bulk is moving, and D is the diffusion field, which describes how material spreads out in space. So for instance, these two cups contain water with different non-isotropic diffusion fields, resulting in the dye spreading out differently in them. Therefore, you could imagine describing the motion of the dye using this PDE with different underlying parameters D for diffusion. In this work, we use a black hole motivated fluid model to parameterize each of the fields with one parameter each, theta 1 and theta 2. By solving for this equation for rho, we can obtain movies that obey this advection-diffusion process under different parameter settings theta. So for instance, for this particular choice of theta 1 and theta 2, when we input some random noise into the process, then it produces a rho that has this swirling structure here. And by tuning these parameters appropriately, you can see that we can produce flow fields from this black hole model that, when paired with a physically motivated envelope, mimic that of a smoothly evolving black hole simulation. So our goal here is then to find the parameters theta that best describe our observed source motion. But there's a catch, and that's that this is a stochastic partial differential equation, meaning that the fluid flow movie we get is dependent on the input forcing term epsilon here. And therefore, if we have two random fields with the same underlying parameters, they're going to still result in very different values of the image over time. So if you look at an individual pixel in both of them, the values are different, although the general flow fields look about the same. The persistence evolution looks similar. Therefore, a key challenge to estimating the dynamics is that the pixel values are driven by this unknown random source, which we don't want to estimate. So an insight of our work is that by using dimensionality reduction, we can ignore this epsilon term altogether when determining the parameters that best fit the dynamics of the random field. So roughly, how does this work? Well, for a given parameter set, we extract the top modes, which captures most of the variability of the stochastic partial differential equation for those particular parameter settings. As we don't actually have access to a matrix operator, this ends up being quite a big challenge in order to get those top modes because we have to use matrix-free methods, which I'm happy to discuss that later if anyone has any questions. But once we have these modes, then we can just compute the projection of the random field onto the subspace spanned by these modes. And if the subspace represents the random field well, then the projection residual will be small. However, parameters that are different from those that generated the random field will result in a subspace that does not capture the random field well, and therefore the projection residual will be high. And so by computing the projection residual for different parameters, we estimate the underlying true parameters as the global minimum to this projection residual loss function. And then we can take this optimal motion parameters, theta 1 and theta 2, that parameterize the velocity and diffusion, and use it to draw a sample fluid flow with the same parameters. And by merging this flow realization with an envelope that we optimize jointly with the dynamic parameters, we can generate a movie that we believe is sampled from a similar stationary distribution as the true underlying video of the black hole. Obviously, these are different. The fluid flow model is not a real model of black hole dynamics, but notice how the video on the right is able to recover like the direction of the flow and also the behavior of the wispy structures. And so the big advantage of this approach is that the parameters we extract are still interpretable while still being somewhat flexible and seeing something surprising. But here, if you paid close attention, you'll notice that I assumed I actually had the true video in order to calculate that projection residual, right? I took my flow field of my video and I said, which parameters of the stochastic PDE best fit that? But we don't actually have the real black hole video in the sky, right? We only have these sparse and noisy measurements. So what are we supposed to do here? Well, actually, it turns out to be a quite simple extension mathematically to optimize in the measurement space. And when we only have measurements to constrain the flow parameters, we can still recover the dynamics decently, even with sparse measurements that mimic those that are captured with a very sparse EHT array. We get the general rotation of the motion. That looks good, but it definitely looks a lot worse than what we saw before. And so as important as it is to continue pushing on the algorithmic approaches like this to squeeze more out of the data, it's also important to realize that to extract more science, we also have to think about improving not just our algorithms that analyze the data, but also our instrument that collects the data to begin with. And to that end, we've been working on improving the actual Event Horizon Telescope network. So in 2017, we only observed with telescopes at 6 different locations, but since then we've been building out our array to get more data, adding telescopes in Greenland, France, Arizona, and then the one I'm most excited about is we recently got funding to add a telescope at Caltech's Owens Valley Radio Observatory, So Caltech is also becoming part of the EHT telescope. But this is really just the beginning. Our goal is to add at least 10 more telescopes around the world, filling up that measurement space so we can get much better data and much better results. And by using the proposed future array, we've been already starting to see that we can improve our dynamic recovery results from something like this to like this, recovering a fluid flow model that's incredibly similar to even the best fitting flow models when we were fitting to the black hole movie directly. And so using this approach, we may be able to not just recover the general structure of the black hole in the center of our galaxy, but actually capture the properties of the gas as it circles towards the event horizon. And I want to highlight here that the reason that this is working is because it's taking the advantages from both imaging, where we have flexibility for that recovering that static image envelope, as well as the advantages of model fitting for the flow field that allows us to take very sparse and noisy data, but because we have less degrees of freedom, we can still recover something interesting about it, like the flow, the direction of flow. All right, so to close, it's clear we've learned a lot from this image of the black hole in M87 already. But what I hope I got across in this talk today is that, really we're just at the very beginning. And now that we have this new extreme laboratory of gravity, we're already thinking towards the future and ways that we can improve our instrument and our algorithms, improve them jointly with the help of ideas from both modern and traditional machine learning to learn even more. And hopefully one day, not just show you a static image of a black hole, but actually a movie of a black hole as the gas is slowly falling towards its event horizon. So with that, I just want to thank the amazing team of Event Horizon Telescope collaborators that I have the opportunity to work with on a daily basis. And in particular, I want to highlight Hassan and Aviad Levis, who have been great and led the two projects that I discussed primarily today.